After looking at the physical representation, we go back to the band diagram. Let's start with an intrinsic silicon, which is represented by a soft, impermeable solid floating on water, with the water level determined by the external potential such as a battery. From the previous videos, you should remember that adding N-type dopants causes the solid to sink, and adding P-type dopants causes the solid to flow. So, the left side is going to flow when it is converted to P-type by doping with acceptors, and the right side will sink if it is doped with donors and convert to N-type silicon. The result looks like what is shown here. Assume the impermeable solid is very soft. A transition region will be formed, which corresponds to the depletion region. The two sides of the transition region that look flat are the neutral regions. When the two sides of the p-n junction have no voltage difference, it is drawn with the two water levels aligned. That also means that the Fermi level of the entire system aligns. This condition is called the thermal equilibrium, and there will be no net flow of electrons or holes. The situation when the Fermi level is not aligned, for example, due to external voltage, will be covered later. I would like to stress the importance of the band diagram, as it represents the static landscape that governs the motion of the carriers. For example, when an electron is placed in the downward sloping part of the band, electrons will simply move downward. Therefore, understanding the band diagram is a very important step to understand the motion of electrons and holes. Given a p-n junction in thermal equilibrium, what do we want to know? There are two important quantities that we'll try to find out. They are the difference between EC or EV on the two sides of the junction, and the width of the depletion region. Once these two quantities are known, we can reconstruct the band diagram easily. Let's look at the difference in EC on the two sides of the junction, which indicates that there is a potential energy difference. We usually call it the built-in potential, and we label it by VBI. This is the potential an electron has to overcome when it moves from the N side to the P side. This is also the force that stops the continuous diffusion of electrons from the N side to the P side. The energy difference is usually expressed as QVBI. To calculate the built-in potential, we add the intrinsic Fermi level of silicon to the band diagram. As the band bending of the conduction band, the intrinsic Fermi level and the valence band is the same. We can see that VBI is just equal to the sum of Vp and Vn marked in the figure. As the carrier concentration in the neutral region is approximately equal to the doping concentration, we can write QVp equal to Kt natural log Na over Ni, and QVn equal to Kt natural log Nd over Ni. Adding the voltages together, we have VBI equal to Kt over Q natural log Na times Nd over Ni squared. This is a very important equation that you should take note of. From this equation, we can easily calculate the built-in potential as long as we know the doping concentration on the two sides of the p-n junction.